Let's take a look now at exercise number 68, an application problem that gives us just one of the many things that we can do with antiderivatives. These have a lot of applications, and you will see more over the course of the next couple calculus classes, in addition to next chapter. But here we have a particle that is moving with the given data, this stuff here. We are asked to find the position of the particle. So we're given a function a of t, implied to be the acceleration function as a function of time. This equals 3 cosine t minus 2 sine t. We're told that s of 0 equals 0, meaning that the initial position is 0, and v of 0 equals 4, the initial velocity is 4. So we have a of t equals 3 cosine t minus 2 sine t. Recall that the acceleration is the derivative of the velocity. So that means that the velocity function v of t would have to be an antiderivative of a of t. So we think about this and try to work out an antiderivative here. We say, okay, we've got a 3. What function has a derivative equal to cosine? Well, that's sine. Sine t has a derivative of cosine. We have minus 2. What function has a derivative of sine? Well, cosine has a derivative of negative sine, which means that the negative cosine, if I switch those signs, has a derivative of positive sine. Alternatively, you could imagine grouping the negative with the sine and say, okay, well, we don't have a function, a basic function whose derivative is sine, but we do have one whose derivative is negative sine. The derivative of cosine is negative sine. So you can move that negative into here, and that becomes a plus in the process. And we mustn't forget our constant. There's going to be some constant that we'll call c. So take a moment to look over this and make sure that its derivative is the given acceleration function. So the velocity function has this general form, but there's an unspecified parameter here. There's an unknown constant c. We use the fact that 4 is equal to v of 0. And v of 0, if you plug that in, that is 3 times the sine of 0, plus 2 times the cosine of 0, plus the constant c. The sine of 0 is 0, cosine of 0 is 1, so this is 2 plus c. And this tells us if 2 plus c equals 4, that means that c must equal 2. So before we had a general form of what the velocity function must look like, and as I said, there was an unspecified constant parameter. We have just solved for that and discovered what that constant parameter is. C we know now to be 2. So this general function that we had, this form for v of t, we've now been able to figure out what precisely v of t must look like. Progress. We want position, however. We recall that the velocity is equal to the derivative of the position function s of t. Or we could call this x if we want to think about that as a position on an x-axis, but s is commonly used. So that means that the original, that looks weird, like a, slightly better. The original position function, s of t, must be an antiderivative of the velocity. So let's do the same thing again. We have a 3. So, okay, what has a derivative of sine t? Well, negative cosine t does. Here's a 2. What has a derivative equal to cosine t? Well, sine t. Now we have 2. Well, whose derivative is 2? Well, 2t. The derivative of 2t will equal 2. And now we have another constant. We can call this d if we want. Or if you want, you could go back and call this c1 and then make this one c2. However you want to do things. We just need different labels for our different constants. So we've got that. Say, okay, well, this is the general form for our position function. What is it precisely? Well, we look at our given data and we see that, oh, the initial position is 0. S of 0 equals 0. So we can say, okay, so 0 is equal to s of 0. But s of 0, we know from here, must be equal to negative 3 cosine 0 plus 2 sine 0 plus 2 times 0 plus d. And this is equal to, so cosine of 0 is 1, so we have negative 3. Sine 0 is 0 times 2 is 0, 2 times 0 is 0, plus d, and this tells us that d is equal to 3, right? If 0 is equal to negative 3 plus d, just solve for d, add 3 to both sides, d equals 3. And now we have the function s of t equals negative 3 cosine t plus 2 sine t, I'm just copying from what I had before, plus 2t plus, and we see it was d, we have just found that d is equal to 3, so we have plus 3 at the end. And this now is the position function. So we see this is extremely powerful. If you've taken a little bit of physics, you have done problems where you're given information like that, and you plug them into a formula, but it usually starts off with a constant acceleration, and then you just plug them into a standard formula and you get your results. That formula only works if acceleration is constant. If acceleration is non-constant, all bets are off. And there are lots of situations where you have non-constant acceleration. For example, if you have simple harmonic motion with a spring, for instance, then the force applied will be a trigonometric function. So this actually, what we have here, I believe we can probably, there might be a way that that can be translated into a single sinusoid, or if not, then maybe it's just a combination of two of them. So this could describe a situation where you have one or two springs attached to an object, and those are governing its motion back and forth. And this would allow us now, you know, the simple standard formula from physics, the one that a lot of you have memorized, would not apply in this situation. But we don't have to worry about that. Once we become comfortable with antiderivatives, we don't need those anymore. We don't need that standard formula. We can just say, okay, here's an acceleration formula, whatever it is. If I can take its antiderivative twice, and I know the initial values to plug in to figure out what the constants are, I'm good. I can just figure out whatever function we have and get a complete description of the thing. And this is just one application. There are plenty of other applications as well. But this is a common, standard, and powerful application of computing antiderivatives given some initial values.